Okay, welcome to Let's Get to the Marks, going through the AQA GCSE Chemistry Higher Tier Paper 2 2024. You've got an hour and 45 minutes. It's 9 questions. Make sure you pause the video at the start of each question. Have a bit of paper, write your answer down. Then unpause and watch the walkthrough. Let's get into it. Okay, Q1. A student investigated an aqueous solution of a salt. The student identified that the salt solution contained only sodium ions and chloride ions. Describe a test to identify sodium ions. Give the result of the test. So I'm going to go through the answers. You might want to pause first and have a go. All right, here we go. You're looking at a flame test. This is where you dip your wire inside a solution, and then you stick it into the luminous part of the flame, or the non-luminous part, sorry, of the flame. And what do we get? We get a yellow color if it's sodium. And I like to think of the S in sodium as kind of like sun. So that tells me we got a yellow flame going on. Right, that's going to get you 2 marks. Let's move on. 1.2. Describe a test to identify chloride ions. Now, a couple of misconceptions here, but why don't you grab a pen, paper, have a go at this. All right, I'm going to go through the answers. So chloride ions, you've got to make sure we distinguish. There's 2 tests, one for chlorine gas and one for chloride ions, and they're different. So if you don't know them and you got this wrong, make sure that you put it on a revision card so that you can learn it off by heart. So the test for chloride ions, we're going to add nitric acid followed by silver nitrate solution. Okay, so nitric acid followed by silver nitrate solution. You probably get them up for just saying add silver nitrate solution. The symbols for these, nitric acid has this symbol, HNO3 with an AQ. So shorthand, this would get you the answer as well. And silver nitrate solution is AgNO3, and that is AQ as well. So that's a shorthand way to write nitric acid or silver nitrate solution. Now, the result of the test is that we would get a white precipitate. Now, precipitate, if you're wondering what that is an insoluble solid. So you'd see a solid form within the middle of the solution that doesn't dissolve. So this would get you the marks. I think you get the 2 marks for silver nitrate solution and white precipitate. Okay, we're on to 1.3. The student determined the concentration of sodium chloride in the salt solution. This is the method they used. Weigh an empty evaporating dish. 2, add 25 centimeter cubed of salt solution into the evaporating dish. Heat the evaporating dish and contents. 4, weigh the evaporating dish and contents. Repeat steps 3 to 4 until there is no further change in mass. 6, repeat steps 1 to 5 3 more times. 1.3, why did the student heat the evaporating dish and contents until the mass did not change? Pause, have a go. All right, this is a sodium chloride solution. What that means is we have sodium chloride and we have AQ. And what is the AQ? The AQ is water. Obviously, what they wanted to do is evaporate the water. And so why would you keep heating it until the weight didn't change? Well, that would tell you that all the water had evaporated. So we call this heating until a constant mass. To make sure all of the water had evaporated. And that'll get us a mark. It's a very common practical technique, so worth getting used to. 1.4, how did the student calculate the mass of solid sodium chloride remaining after steps 1 to 5? Mass of 25 centimeters of the salt solution plus the mass of the empty evaporating dish. They want to calculate the mass of the solid sodium chloride. So why would they use the mass of the salt solution? Because that is including the water. That's not going to be just the mass of solid sodium chloride. So we can get rid of this one as well, because that is including the salt solution. The mass of the evaporating dish and the dry contents, which would be the salt, plus the mass of the empty evaporating dish. That sounds a bit dodgy, doesn't it? Like if you wanted to know the mass of the salt, why would you include the mass of the evaporating dish? That the evaporating dish isn't made of salt. So this one is going to make sense. The mass of the evaporating dish and the dry contents, so the dish and the salt, take away the mass of the evaporating dish. So you're looking at dish, essentially translated, what this means is dish plus salt, take away dish equals salt. And that makes sense. So we're going for that one there. All right, let's move on. Right, we're looking at 1.5. The student calculated the concentration of sodium chloride in the salt solution. Table 1 shows the results. Here's table 1. Concentration of sodium chloride in grams per decimeter cubed. Trial 1, 35.2, trial 2, 34.6, trial 3, 36.4, trial 4, 33.8. The percentage by mass of sodium ions in the sodium chloride is 39.3%. Calculate the mean concentration of sodium ions in the salt solution. So we've been told the amount of sodium ions in the sodium chloride is 39.3%. Calculate the mean concentration of sodium ions in the salt solution. So what we need to do is work out, first of all, the mass of sodium chloride, and then we know the 39.3% of the mean of this is sodium ions. So essentially, they're getting you to calculate a mean, that skill, and then they're getting you to see if you can multiply by a percentage. Let's do it. So we want to go 35.2 plus 34.6 plus 36.4 plus 33.8. We want to add those all together and then divide by, not 0.4, we want to divide by 4. I'm going to smash that in the calc and then we'll find out what we've got. And then I realize I haven't got my calculator. Give me 1 sec. Okay, so if we add these all up and divide by 4, we get 140 for the total of that, but that's before I've divided by 4. 140 divided by 4, which equals 35. So what we've worked out is that the sodium chloride solution, the NaCl, equals 35 grams per decimeter. Now they're asking us, what is the, well, we know the percentage of sodium ions. Now sodium ion is different because it's lost an electron, so it's an ion. Right, now we know that of that, 39.3% is sodium ions. So I just need to do that times 39.3. So we're going to do 39.3 over 100. When you multiply by a percentage, you divide the percentage by 100 and then times 35. And whatever the hell that is, so I'm going to times 0.393, and that equals 13.75. And there we go. 4 marks. Beautiful. 1 for adding those all up and working out 140, 1 for working out that as 35, 1 for doing the percentage times that, and then 1 for the correct answer. Now, is it to 1 decimal place? No, we could round that up to 13.8 if we wanted to go to 1 dp. Okay, nice. Let's move on. Right, we're on question 2. This question is about ammonia and nitric acids. So in the Haber process, ammonia is produced from nitrogen and hydrogen. Figure 1 represents the Haber process. Figure 1, nitrogen gas, hydrogen gas. We've got a reactor at 450 degrees, 200 atmospheres, metal catalyst. Then we've got a condenser. So what's going on here? We've got a reactor, it's 450 degrees, and we've got 200 atmospheres, and we've whacked the metal catalyst in there. We've got the nitrogen gas, the hydrogen gas coming inside there. Then something's happening in there. They're going to a condenser. Guess what's going to happen there? Liquid ammonia comes off. I guess it condensed, and then something is going through pipe P back into this reactor. Okay, pipe P links the condenser to the reactor. Question 2.1, why is the condenser linked to the reactor? So what happens here is, so ammonia can be turned from a gas into a liquid to get the product away from excess reactants. So essentially in the Haber process, ammonia will become, if you cool the mixture of hydrogen, nitrogen, which has gone in here, first of all, it's heated up to 450, it reacts to form NH3. So what you've got going on, you've got N2 plus like 3H2, they're coming in here, they're making 2 NH3. But of course, you don't just have ammonia, you still have some leftover nitrogen and hydrogen bobbing about in there. Now they're all gases, all 3 of these are gases. So we cool it down, and the first one to turn to a liquid is ammonia, so we can peel that off. And as long as we don't cool it too much, nitrogen and hydrogen will stay as a gas, and guess where they'll go? Okay, coolio. Right, let's move on. Oh my gosh, I'm ticking everything. Jeez. Right, let's check out 2.1. Which metal is used as a catalyst? So in the Haber process, there are some conditions you need to know off by heart. 450 degrees, you don't need to put that here, but you also need to know that it's done at a pressure of 200 atmospheres, and then you need to know the catalyst, and the answer they're looking for is iron catalyst. So iron is the metal that they use in the Haber process, and you just need to put iron there. Nitric acid is produced by reacting ammonia with oxygen. The word equation for the production of nitric acid is ammonia plus oxygen goes to water plus nitric acid. Platinum is the catalyst in this reaction. Describe the test for oxygen gas. So after all of this, they just want us to give the test for oxygen gas. You've got 4 tests or 5 gas tests you should know off by heart. And if you don't know them, grab a revision card, write down what's the test for hydrogen, what's the test for chlorine, what's the test for ammonia, and what's the test for oxygen. Did I say carbon dioxide as well? So hydrogen, chlorine. So it's 5: hydrogen, chlorine, ammonia, carbon dioxide, and oxygen. You got to know those 5 gas tests. Well, the gas test for oxygen, if you've already been thinking of it while I've been waffling, the test is um, put a glowing splint at the end of test tube. Yeah, that's if your reaction's happening in a test tube. Depends where your reaction's happening. What is the result? It will relight. So it will relight a glowing splint. Essentially, you got to know that off by heart. For chlorine, just to quickly go through the gas tests, chlorine will bleach litmus paper red, then white, but the essential bit is just to know it bleaches litmus paper white. Ammonia, the gas test for ammonia is to check you've got ammonia gas. It smells fishy. You can just go with that. Turns damp red litmus paper blue. That's another one for ammonia. The test for hydrogen is the squeaky pop test. So you put a lit splint at the end of the test tube and it goes pop. Carbon dioxide turns lime water milky. I think I covered them all there, right? Yeah. All right. Anywho, you can look those up, get those down, get them on a revision card if you don't know them. One of them is definitely going to come up in your GCSE exam. Figure 2 represents the reaction profile of the catalyzed reaction between ammonia and oxygen. Energy, progress of reaction. We've got 2 blank flat bits there and a dotted line under the hump. Figure 2.5. How would figure 2 be different if no catalyst was used? Oh, sorry. 2.4, complete the reaction profile for the catalyzed reaction in figure 2. Label the activation energy, label the reactants and the products using the name of the reactants and products. Okay. So this reaction has used the catalyst. And so what we want to do here is write reactants, and that's going to get us a boom, a mark, hopefully. Products. This is exothermic, this reaction. The reactants are higher than the products. Some of the energy has been lost. Now, this is the activation energy. I'm going to label the activation energy E for energy A, energy of activation. You can write AE, or you could just write activation energy. And then the energy of the overall reaction energy, which is like the enthalpy change, you can write triangle H, or I'm just going to put overall energy change is this line going down. Why does the arrow go down? Because it's exothermic. Energy has gone down from where it was originally. So that's that fully labeled. That will get you all the marks. Again, you can make a revision card where you put that on one side and then say label this up. And then on the other side, you have the labeled version. Using the names of the reactants and products. Oh, dear, oh dear. I need to put ammonia, oxygen, and water and nitric acid. That's a pain in the ass. Right, let me go back and put that correct for you guys because I didn't read the question properly. So what we're going to do here, we're going to go bosh, bit. Oh, geez, Louise. How'd I put my rubber there and that thing? Anyway, let's not worry about it. Now, what was that? Ammonia plus oxygen. And what did it make? It made water. Oh my gosh, I've forgotten what the other thing it made. Ammonia and oxygen is going to make water and nitrogen, right? Water and nitrogen. I'm going with it. Water and nitrogen. I know, dear. Okay, so ammonia plus oxygen makes water and nitrogen. There we go. Let's just check that was right. No, it was water and nitric acid. Why would they be making the nitrogen? Okay. I couldn't be bothered to look back up there. I should have done. Memory like a sieve. Everything just slips through the holes. I've done it again. So it's nitric acid. Yep, that's it. Guess that's gonna be 1, 2, 3, 4. Should be 4. They're probably giving you 2 marks for this thing. All right, let's scroll. 2 marks, chieftains. Right, 2.5. How would figure 2 be different if no catalyst was used? So if there was no catalyst, the final energy level would be higher. The final energy level would be lower. The line would reach a higher peak. The line would reach a lower peak. So the answer, of course, is the line would reach a higher peak. So this would be the catalyzed reaction. And if you didn't have a catalyst, the activation energy required is going to be higher, but the overall energy change would be the same, but you're just putting more energy in, so it's more expensive, costing you more money without a catalyst. Okay, let's go. 2.6. Ammonia and nitric acid react to produce the salt ammonium nitrate. Ammonium ions and nitrate ions both contain nitrogen. Suggest one use of ammonium nitrate. Ammonium nitrate is used as fertilizer or to make fertilizer. To make fertilizers. There we go. Okay, let's go. Question 3. This question's about water. 3.1. Hydrogen gas reacts with oxygen gas to produce water. Water is decomposed into hydrogen gas and oxygen gas using electricity. Which two words describe the reaction between hydrogen gas and oxygen gas? So if you think we're going H2 plus O2, and that makes water, balance this bad boy up. So I'd need 2 there and a 2 there. Right. What two boxes? Is this alloying? Is that an alloy? Is water an alloy? No. An alloy is a mixture of a metal and another element of different sizes in a mixture. Combustion. Well, combustion is burning in oxygen. Um, yeah, I think we might go with combustion until I see it elsewise. Corrosion. Corrosion is the oxidation of a metal. Now, some people do put hydrogen in the metals in the periodic table, some weirdos. Well, it kind of has the electronic structure of metals, but we're not going to go with that. Is the reaction endothermic? Does this release, does this take in heat? No, this is a combustion reaction. It releases heat. When hydrogen and oxygen are together, you'll get light, you'll get heat released as the water is formed. So it's not endothermic. Is it reversible? Well, look what they say here. Hydrogen gas reacts with oxygen to make water. And then they say water goes to make hydrogen and oxygen in the other direction. So yes, this is a reversible reaction. And the symbol is like that. Not this one I've done here. There you go. So yes, it's reversible. Combustion and reversible, 2 marks. Okay, water molecules break down into hydrogen ions and hydroxide ions. The equation is this: H2O reversible, hydrogen ions, hydroxide ions. Which sentence describes this reaction at equilibrium? Is there another box on the next page? Because that'd be just done. No, there isn't. Thank you for not being so dumb. Water molecules break down at a higher rate than that. What sentence describes this reaction when it reaches equilibrium? Do the water molecules break down at a higher rate than they reform? Well, that wouldn't be equal, would it? So that's not equilibrium. Water molecules break down and reform at the same rate. That sounds pretty equal to me. Let's check the next one. Water molecules break down at a lower rate than they reform. No, that wouldn't be equal. So equilibrium is when the forwards and backwards reaction occur at the same rate. So as each water molecule breaks down this way, one hydroxide and hydrogen are joining together to make water that way. 3.3. Water collected from rivers is used in the home for drinking and flushing toilets. Water used in the home must be potable. Potable water is safe to drink. Wastewater produced after use in the home is called sewage. Figure 3 shows how water is collected from rivers and returned to rivers after use. So we've got water used in the home, goes down your toilet or down the shower, down the bath, sink, into the sewage. Process B, treated in the sewage. Here's the treat. There's a grid treatment. There's a grid. We got these dots here. We got this effluent, and we got some sludge coming out, and then we got the effluent put back into the river, and then it rains groundwater, and we use potable water. That means water we drink, cook our rice in, make our tea with, and used in the home. Lovely. And then we wee that out again. Okay. Explain what happens to water in process A and in process B in figure 3. Do not refer to the use of water in the home. All right, wait while I drink some coffee. Okay, let's smash this out then. So we literally have to explain process A, groundwater. How do we produce potable water from groundwater? So actually, I might come and write my answer up here. It's 6 marks, but I'm going to write my answer up here. Okay. So bear with me, peeps. So we're just explaining process A and process B, and you're going to get all the marks for explaining these processes. So where am I going to write this? I've not really left myself any room. All right, let me shrink this down so I've got a little bit more room. And I'm going to write this over here. So for process A, how do we produce potable water? The first thing we're going to do is filter the groundwater using what do we want to use? Pebbles and sand. So filter the groundwater using a mesh. I'm going to say to remove twigs, sticks basically, and bits. Pebbles, use pebbles. Oh my gosh, I'm making this really long. Use pebbles and sand to filter small insoluble solids out. Then what do we want to do? We want to use chlorine or UV light or ozone to sterilize the water to kill microbes. I'm sure I've missed a step out, but remember, with all these things, you don't need everything to get all the marks. So I might move that down onto my answer in a bit, but essentially that is how we're making potable water. So we're going to filter the water using a mesh to remove large bits. We're going to then use pebbles and sand filter to filter out the small insoluble solids, bits of grit and dirt that are too small to get caught by the mesh. We're then going to hit the water with chlorine or UV light or ozone, and that will sterilize the water. It will kill any germs, and now it is safe to drink. And this is slightly different than process B. So we're going to have a look at process B now. So for process B, we're going to take the sewage. So sewage is filtered or screened, they call it, with a mesh to remove large debris. So again, we want to remove sticks, rubbish, litter, anything that's in there with the metal grid. We're then going to leave for solids to sediment at bottom of tank. This is called sedimentation. So we're going to wait for all the solids to fall to the bottom of the tank. We call that sedimentation. It will divide into effluent and sludge. So it splits then into the liquid waste and the solid waste. What we're going to do with the effluent is digested in aerobic, biaerobic bacteria, and the liquid water is recycled back into rivers. The solid sludge, that's your poo, that's your feces. The solid sludge is digested by anaerobic. They're bacteria that don't like oxygen. So I've really effed the spelling up there. Right, hold on. Anaerobic, there we go. The solid sludge is digested by anaerobic bacteria and is turned into fertilizer or manure, basically to put onto plants and help them grow. And there we go. I reckon that's going to be enough to get us the 6 marks, right? Now, I know there's probably some little bits of the process that we've missed out, but we're going to put that together to make our 6 marker. So I'm just going to scroll down the page and then lick them on the page. On my toes. Obviously, I wouldn't recommend writing them like this in 2 boxes, but I needed to keep that information so that I could not have to scroll up and down. So this would be like process A, and I'm explaining it. If I was just describing it, I'd describe it. I wouldn't say to kill the microbes, I'd just say use UV light. I'd just say filter, I wouldn't say to get rid of insoluble solids. Yeah, coolio. I reckon that's good enough. Let's go. Right, question 4. A student investigated an orange dye A using paper chromatography. Figure 4 shows the results of experiment 1 and experiment 2 using orange dye A. So we got experiment 1 and experiment 2. They put orange dye A on there, and it's obviously split into different colors. Explain why the yellow and red dye travel different distances in experiment 1. Refer to the forces of attraction between the dyes and the chromatography paper in your answer. So what we're looking at here, we've got water, we've got a start line. There was an orange dye A that was put there in the middle of the start line, and it's split into the different dyes that it's made of, and they move at different speeds up the paper. And they're asking us to say, why did they travel different distances? Refer to the forces of attraction. So what we're talking about here, guys, is actually, I'm just going to put it all on here. It's only 2 marks. So we're going to put this here. The yellow dye had a greater force. They've asked us to use this language. I wouldn't normally say this, but a greater force of attraction to the solvent, that's the water, right? In this case, the water, a greater attraction to the solvent than the red dye. The red dye had a greater force of attraction to the paper than the yellow dye. So this is actually, sometimes we use the word affinity. So we would say that the red dye had a greater attraction or a greater affinity to the mobile phase, which is the water, than it does the stationary phase. Therefore, it has not moved as far, whereas the yellow dye had a greater attraction to the mobile phase or a greater affinity, which is like the force of attraction to the mobile phase than it does to the stationary phase, which is the paper. But anywho, there we go. Let's smash that there and there. Easy peasy. Let's go. The student used the same chromatography paper in experiment 1 and 2. Explain why the yellow dye is in different positions. What did you think they did differently then? Why is the yellow dye moved differently in experiment 2? Let's have a look and see what they did differently. Aha. They used ethanol. So we want to say they used a different solvent. And what does it tell us about the yellow dye's force of attraction to ethanol compared to its force of attraction to water? So it looks like the yellow dye is more soluble in ethanol than it is in water, or has a greater force of attraction to the ethanol than it does the paper compared to the water in the paper. Anywho, that's all long. Let's put the answer down. So the yellow dye traveled, oh my days, Louise, traveled further in the, oh my days, ethanol than the water. It was more soluble in ethanol than water. It had a greater attraction to the ethanol um, compared to the filter paper than it did uh, in water. So it's more attracted to the ethanol than it is to the water, more soluble in the ethanol than the water. Therefore, it traveled further in the same amount of time. God, that's a bit of a long one to write, but yeah, I probably could have talked about mobile and stationary phase there and said the yellow dye, it had a greater affinity to the mobile phase than the stationary phase. So greater affinity to ethanol than to water. And then you could compare it to the stationary phase if I really wanted to, but that's just long. Figure 4 is repeated below. Figure 4 shows the results of experiment 1 and experiment 2 using the orange dye. Okay, that's exactly the same as we've had. The student used a different orange dye, B. Figure 5 shows the results of experiment 3 using a different orange dye, B. So the orange dye is bang in the middle of the paper, and you can see they used ethanol this time. Compare the purity of orange dyes A and B. Give reasons for your answers. Right. Okay. Hopefully I wasn't talking about A and B in the previous thing. But anyway, so what we want to say is, if you have a little look, let me just talk you through it. And so if you have a look at orange dye A was made of two different things because it's split into yellow and red dye. So it's not as pure as orange dye B. Orange dye B appears to only be made of one color, but we can't 100% be sure about that because we haven't tried it in water. Maybe the dyes that are inside that orange dye are not soluble in ethanol, but if that was the case, I guess they'd be left on the line. So no, we can say it is pure. It's only made because it is soluble because it's moved up the paper, but it's only made of one substance. Okay, cool. So what we want to say is orange dye B is purer as it is only made of orange dye, whereas orange dye A is a mixture of yellow and red dyes. Okay, wunderbar. And I guess, yeah, that'll do. Let's go down. The student calculated the RF value for the orange dye in the experiment showed in figure 5 as 0.48. Calculate the distance moved by the solvent front when the orange dye was moved 5.4 centimeters. So we need to calculate the solvent front. Now, there's the solvent front. They're saying this has moved 0.48, the orange dye, and that's the solvent front. And they've given us the RF value. An RF value is a measure of the distance moved by the orange dye when compared to the solvent front. So there's a little equation, and you should know it off by heart. And you just got to rearrange it. And it's basically like this. RF value is equal to distance of dye divided by distance of, or divided by the solvent front. Now, I haven't written that all in the perfect language, but you know, who gives a monkeys? So we're going to rearrange this. The bit we don't know is the solvent front. So we want to do the distance of the dye divided by the RF value. Now we'll know we've got it wrong if the distance of the dye comes up less than the solvent front must always be bigger than the distance of the dye. And we know it's moved roughly 50%. So we know the solvent front is roughly double that. So we're going to go 5.4 and we're going to divide that by the solvent front, because if you rearrange this or put this in a triangle, whatever's above the divide line will be at the top. So I'm going to do, I'm not going to do it there because it looks a bit weird. I'm going to do 5.4 is equal to 0.48 divided by our mystery thing. So we can just do, no, I've written that completely wrong, haven't I? What a twit. What a twithead. Yeah, I did have a W in there. Right, 5.4, and we want to go 0.48. And so 5 point, oh my gosh, I'm longing this out. Jeez. Oh my days. 5.4 divided by 0.48 equals 11.25. So we're looking at 11.25. There we go, folks. Bish bash bosh. 3 marks. So I guess one for substituting everything in, one for coming up with that, and one for doing a handstand. Right. Okay. 4.5. Why is the RF value of a dye not affected by how far the solvent front is allowed to travel? Essentially, essentially, um, the solvent front is always moving and the orange dye is always moving. The solvent front doesn't stay still while the orange dye moves up. That's the water line. So the water is going to keep moving, or the ethanol line in this case. The ethanol is going to keep moving up the paper and the orange dye is going to keep moving up. And they're at a constant. So they're moving at the same ratio between them in their distance they're moving. So what we want to say is the distance moved by dye is in proportion to distance moved by solvent. Um, the RF value is just ratio of distance moved of solvent um, over distance moved of dye. They both keep moving basically at the same constant. Okay. Oh my gosh, this question never ends. 4.6, another type of chromatography is called gas chromatography. Gas chromatography is an instrumental method of chemical analysis. Scientists tested the orange dyes using gas chromatography. State two advantages of using instrumental method of gas chromatography rather than paper. Okay, so gas chromatography, it's a little bit different. What we do is we kind of vaporize. So say here's my liquid dye. I vaporize it into a gas. It's then passed through a tube, which is filled with gel. Oh my God, that is the crustiest tube ever, but you get the idea, kind of, sort of, maybe. This tube is filled with gel, and then we time how long it takes to come out. How long it takes for the substance to come out, our gas, and different gases will move at different speeds or rates through the stationary phase. The stationary phase is the gel, I guess, or whatever. Yeah, whatever we're talking about here. So anyway, and there's some sort of carrier gas, I guess it's the mobile phase or something. Anyway, the point is that with this, because you're vaporizing things into a gas, you can use tiny amounts. It's very accurate, it's very sensitive, which means, so I'm going to put it is very sensitive. So you can use like just 1 gram of a substance. It's what they use in those airport shows where you see people when they stop them and they find they've got cocaine or other drugs in their luggage and they put it in a machine and it goes beep, 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 this is cocaine or whatever. Yeah, so it's very sensitive. You don't need very big amounts because you're just vaporizing it into a gas. It's also very accurate. It is very accurate. So it's far more accurate. You're going to get a much more exact number than the RF value you get with chromatography. You're not doing centimeters here. You're talking really high levels of accuracy. And here we go. It's also far quicker as well. So I could put it's faster. That gas is going to move a lot faster than some dyes will move up a paper. If you've ever done chromatography, you've got to wait about 10 minutes, 15 minutes for the inks to crawl up the paper. It's a right pain in the butt when you're trying to demo it to a class. So you could put it is faster. Right, we're on question 5. This question is about burning fuels in central heating boilers. In the future, gas central heating boilers may burn hydrogen rather than natural gas. Table 2 shows the information about these fuels when 1 decimeter of the fuel was burned in a central heating boiler. So we've got the fuel, we've got hydrogen, we've got natural gas, energy released in kilojoules. So natural gas releases a lot more energy. Mass of carbon dioxide, the hydrogen doesn't give off any, but the natural gas does. Mass of water vapor produced, lots of water made by the natural gas, not a lot made by hydrogen. Mass of the oxides of nitrogen produced. So 6.6 times 10 to the minus 4 compared to 4.9 times 10 to the minus 4. Right, explain how the oxides of nitrogen are produced when burning fuels. After all of that, I thought they were going to get us to compare. How are oxides of nitrogen produced when burning fuels? So where do you think nitrogen comes from? Nitrogen is in the air. So we're going to say nitrogen in the air reacts with oxygen in the air on a hot surface to form nitrogen oxides. So that's how it's produced. You need heat from hot metal or a hot surface, which you get when you're burning things in a boiler, and you've got oxygen and nitrogen already in the air, 78% nitrogen, 21% oxygen. The air is, they come together and they react on very hot surfaces, and you get nitrogen dioxide, trioxide, or monoxide formed. Okay. Explain one positive impact on the environment of burning hydrogen rather than natural gas as a fuel. So I think you can remember that when we looked at the table, it didn't produce, so it does not produce any carbon dioxide, which is a greenhouse gas, so will have a reduced effect on global warming. It's basically not making global warming. It's not making as much greenhouse gases, okay? Or not as much carbon dioxide anyway. It makes more water, which is a greenhouse gas, but it's not as powerful a greenhouse gas as carbon dioxide. So explain one negative impact on the environment of burning hydrogen rather than natural gas as a fuel. So if we zing up here, I believe it made more nitrogen oxide. It does. It makes more nitrogen, more oxides of nitrogen, and they cause acid rain, or they can cause respiratory issues. So we're going to say it produces some nitrogen oxides, which can cause acid rain, which kills trees, um, changes pH of soil and water, also causes, I'm just listing all of them, you wouldn't need to put all of these, respiratory problems. So it's been linked to asthma and other breathing issues, nitrogen oxides. Okay. 5.4, air is 20% oxygen, 21 more like, but never mind. Air is 20% oxygen. Calculate the volume of air needed to provide enough oxygen to react with 3.5 decimeters of hydrogen gas. The equation of for the reaction is 2H2 plus O2 goes to 2H2O. So what they're telling us is that the volume of air needed to provide, so we've got 3.5 decimeters of hydrogen gas. So I would go like this. You got 3.5 dem. Now, we can deal with this after rather than before. So we can deal with that after. So we've got 3.5 M. What you do is you look at the ratio. So for every 3.5 hydrogen, because it's a 2-to-1 ratio, I'm going to need half the amount of oxygen. So what I'm going to do is divide this by 2. So we're going to go 3.5, let me calculate wrong with help, 3.5 divided by 2 equals 1.75. And this will have got you hopefully 2 marks. Out the 3. So you're going to need 1.75 decimeters of oxygen. However, it's asking us not for how much oxygen, it's saying calculate the volume of air needed. Now, in order to get 1.75, bearing in mind this is 1/5 of air, this is 1/5. I'm going to need 5 times that amount of air. So how much air would give me 1.75 oxygen? Well, bearing in mind that's only 20%, I need 5 times that amount of air. So I'm going to times by 5, and that's going to give me the volume of air. So in 8.75 decimeters of air, I'm going to have 1.75 decimeters of oxygen, which can react with that hydrogen. So it's going to be it's going to be 8.75. Okay, so that should get you 2 marks, and then times by 5 should get you the full fat 3 marks. Obviously, you're going to need more air than oxygen. So central heating boilers can also burn kerosene. That's like an aeroplane fuel. Kerosene is produced from crude oil in a fractionating column using fractional distillation. In the first step, crude oil is heated and the hydrocarbons vapors are formed. Explain how kerosene is produced from these hydrocarbon vapors. So this is quite easy. We just want to say the hydrocarbon vapors rise up the tower. So they rise up the tower or column. The column has a temperature gradient. Now, what we're explaining here, they're basically saying talk about fractional distillation, and you should know you've got fractional distillation looks like this. You've got a column, it's got different bits. I'm not going to draw all the bits, so let's just do it like that because we don't want to waste too much time. So in goes the crude oil. They've already told us it's vaporized, it's heated here. Okay, that's where it gets heated. It turns to a vapor, it rises up the tower. Once it reaches the boiling point of kerosene, it's going to condense and you're going to be able to tap it off. Okay. And it's based on the fact that all the different fractions have different boiling points. We have to understand as well that the tower is hot at the bottom and cold at the top. So it's been vaporized. It rises up the tower from hot to cold. And we're saying that the hydrocarbon vapors rise up the tower. The column has a temperature gradient. And I'm just going to say it is hot at the bottom and cooler at the top. As it rises to an area at its boiling point, it condenses back into liquid kerosene, and is tapped off or poured off. Okay. Now, I don't know whether we needed to talk about any of the intermolecular forces, but we're not going to bother with that. So the key kind of points are really, I guess, that it rises up the tower. The tower is hot at the bottom and cooler at the top. Once it reaches its boiling point, it condenses. So These first two might combine to make one mark and then hits its boiling point, condenses back to kerosene. Okay. And the word condenses is going to be a key science word they want there, and boiling point. Question 6, the question's about materials used to make bicycles. Figure 6 shows a bicycle. So here's our bike. We've got a chain, we've got a frame. Table 3 shows information about two materials used to make the bicycle frames. So we could make it out of alu. Yeah, make it out of potato, guys. Make it out of aluminium alloy or bamboo. Raw material, aluminium ore or bamboo plant. Cost of the frame, 250, bamboo, 1,500. Gosh, expensive for bamboo bike. Strength, 290, 193. So your aluminium is stronger and cheaper. Mass in kilograms, your aluminium is lighter than the bamboo. Lifespan in years, 6 to 10. The bamboo lasts a lot longer, 10 to 15. One method of disposal, recycle to make new products, burned to produce heat energy. Okay, cool. Evaluate the use of aluminium alloy and of bamboo for making bicycle frames. All right, guys, what this is about is basically saying, say some good stuff about aluminium and say some good stuff about bamboo, and then say some bad stuff about both. Like do a comparison as you go. This is better for that. This is better for that. And then basically make your final decision about which one you think is better and save something cool to say in your final statement. So plus and negative for each, and then something cool at the end. So I'm going to go piece by piece, and I'm going to shrink this down, and I might put my answer here. It's a little bit crap here, but there we go. Let's put it here. Right, aluminium alloy, raw material aluminium ore, bamboo plant. So I'm going to say aluminium ore, which I can't spell. I'm just going to use this chemical symbol. Al ore is non-renewable resource, whereas bamboo is a renewable resource. So that one wasn't really told in the table. You had to work that out just by looking at it. That's a plant, that's an aluminium ore. So this one I'm not expecting everybody to get. Aluminium ore is a non-renewable resource, whereas bamboo is a renewable resource. So it will not run out. So that is a big fat tick in favor of using bamboo. Now we're going to say the cost. Aluminium is cheaper and more affordable than bamboo. Why is that better? That means that poorer people or people with less money can have a bike, essentially. So that's a good thing on the right, because you don't want just rich people riding around on bikes. £1,500 for a bike frame. Strength in arbitrary units. The aluminium is also, so we want to say aluminium is also stronger. So could hold heavier riders or and more weight. Basically, if you're heavier, you'd want to pick the aluminium one, and it can hold more weight if you've got your shopping on there as well. So that's another tick for aluminium. Then we're going to come down here. The mass in kilograms. Aluminium is also lighter. It's all looking aluminium right now to me. Aluminium, unless you're really with the environment and you're saying, well, it's non-renewable, which is fair point. Aluminium is lighter, so easier to lift and carry. So we want to say aluminium's lighter, and then why is that important? Well, it's easier for you to pick it up and carry it about. And then the lifespan, however, bamboo lasts longer. Bamboo lasts longer. Um, so would not need to be replaced as much. I mean, that's a big tick for bamboo. But what I would say on that, if I was coming to my conclusion, which I'm getting to now, you could potentially go with your conclusion that, hey, look, yeah, bamboo is stronger, but because it is, what, 7 times more expensive, you could do a bit of maths, 1,500 divided by 250. No, I don't even know what that is. What is that? I'm going to have to bust the calculator out. I'm not smart enough for that. 1,500 divided by 250 is 6 times, sorry. So bamboo is 6 times longer. This only lasts like twice as long but costs you 6 times more. So be like, okay, so my aluminium bike is I could buy 3 aluminium bikes and they're going to last a lot longer and be cheaper. So that would be a nice sum up for an evaluation to say, look, I know aluminium doesn't last as long, but I could get 6 bikes for the cost of a bamboo bike. Bosh. Right. One method of disposal is recycled to make new products or burned to produce heat energy. So, yeah, we can compare that. So recycling, I don't know what we'd say. Recycling is better for the environment, is better for environment, um, but uses energy, whereas burning is going to produce CO2. You can't get away from it. If you burn something, you're going to produce carbon dioxide. Um, however, is carbon neutral as bamboo photosynthesize. So when the bamboo plant is growing, it's sucking in carbon dioxide. So when you burn it and release that carbon dioxide, you're not really overall changing the environment that much, and you're getting some heat energy. Also, the heat produced can be used to heat homes. Like, so you could burn the bamboo bikes and you could use that to heat home, keep yourself warm, and all that kind of thing. So if I scroll down, I'm going to make my final thing on this. So here we go. So we're going to put our final stamp on it. Now, what I would say, oh my good gosh, is it's good to put a final conclusion. So I'm just going to squirt this up. Oh my days. What's going on there? All right. Oh, it's kind of all gone all over the place, folks. The ticks are everywhere. Don't worry about the green ticks. Oh, what have we done here? This is painful. Oh my God. Call the doctor. And in my final conclusion was going to be like, I prefer aluminium as it is 6 times cheaper. So could buy 6 bikes for price of one. And there's an argument there, people to say, oh, the bamboo's a lot greener, it's a lot better for the environment. But you say, well, is it really? Because you're going to need to use you're going to need, for every one bamboo bike, you can give 6 people an aluminium bike. So, you know what I mean? You got to weigh that up, weigh that up. All right, that will get us 6 marks. Explain why aluminium alloy bicycle frames do not need protection from corrosion. So, yeah, aluminium alloy bicycle frames do not need protection from corrosion. Aluminium oxide layer forms. This is unreactive. Aluminium oxide is a tough, unreactive layer. So aluminium does kind of corrode. It forms aluminium oxide, but unlike iron oxide, which is an orange brittle substance, aluminium oxide, which is a kind of silvery white substance, is very tough, high melting point, very unreactive. So it's actually a good thing to form an aluminium oxide layer. Okay, let's zing, which is why we use aluminium on window frames, and even your pencil sharpener is probably made of aluminium. And when you look at it, when you take it out of the packet, it's got like a white silvery shine on it. That's aluminium oxide. Bicycle chains are made from an alloy of iron. Bicycle chains rust without protection. Paint is not used to protect bicycle chains from rusting. Suggest how bicycle chains can be protected from rusting. So what we do with bicycle chains, oil the chain. And it's simple as that. You put oil on the chain and it prevents the oxygen getting to the iron and forming iron oxide, and water from getting to it, because oil repels water. Painting just, you get too much friction. It wouldn't reduce the friction, which oil also does. 6.4, bicycle frames can also be made from a composite of carbon fibers embedded in a polymer resin. What description is given to this composite? The carbon fiber component, the polymer resin component. So, the polymer resin is the binding agent, and the carbon fiber is the reinforcer that makes it strong. So this is the reinforcement for strength. So this makes the bike strong. And the polymer resin, this binds the fibers together. So this is the binding agent, the binding agent. The bonding agent? Yeah, the binding agent. Okay, mishmash. Right, we're moving on to question 7. Oh my gosh. This question is about sulfuric acid. Sulfuric acid contains sulfate ions. Describe the test for the presence of sulfate ions in sulfuric acid. Give the result of the test. So you can pause the video, have a go. Here's what you're going to do. You're going to add barium. Oh, well, first of all, you're going to add hydrochloric acid, then barium chloride. The positive result of the test would be barium sulfate forms, which is a white precipitate. Now, what do you actually need to put to get the marks? You just need to say add barium chloride, and you'll get a white precipitate. But I like to explain a little bit more detail. You should add the acid first to get rid of any carbonate impurities. All right, let's go. One stage of the industrial production of sulfuric acid is the reaction of sulfur dioxide with oxygen to produce sulfur trioxide. This is known as the contact process. This reversible reaction reaches a dynamic equilibrium. Let's zoom in. Figure 7 shows the percentage yield of sulfur trioxide in this reaction at different temperatures. So you've got the percentage yield and you've got the temperature along the bottom here. Let's go. Which statement about the forward reaction is correct? The yield is greater at higher temperatures because the reaction is exothermic. The yield is greater at higher temperatures because the reaction is endothermic. The yield is smaller at higher temperatures because the reaction is exothermic. The yield is smaller at higher temperatures because the reaction is endothermic. So we'll have a little look. Does it tell us anything about the reaction? No, just as different temperatures. So the percentage yield, we get the highest percentage yield of sulfur trioxide at lower temperatures. The higher the temperature, the lower the yield. And what does that tell me? If I'm increasing the temperature and the reaction is doing the reverse, it's going to the endothermic side. So that means it's going to the endothermic side, which means the yield is smaller at higher temperatures because the reaction is exothermic. That is the answer. And that is why we can get rid of this one. The yield is greater at higher temperatures. No, it's not. The yield is not greater at higher temperatures. We saw when we get to the high temperature, the yield was low. We could see that on the graph. So the reason why it's low is because essentially with Le Chatelier's principle, if you have a reaction that's endo on the reactant side and exo on that side, if you make it hot, the reaction is going to go to the cold side, the endo side, and lower your yield. So it must be an exothermic reaction. Anywho, let's zing on. Push, bish, bash. That's quite hard, I know. Right, here's the equation for the reaction. Two sulfur dioxide molecules in gaseous form plus oxygen gaseous, reversible symbol, two trioxide gaseous. Explain why the percentage yield of sulfur trioxide in this reaction is greater if the pressure is higher. So what we want to do here, when we're talking about pressure and we're talking about yield, what we need to do be looking at reverse is count up a reversible reaction, count up the gas molecules on each side. So we've got one, two sulfurs and one oxygen. That's three. And then on this side, we've got two lots of sulfur trioxide. That's two. So you're just counting up the big numbers. You're not looking at these little numbers or anything like that. So you're just looking at the big numbers. You've got a big two there and a one essentially there. So that's three. And we've just got a two there. So it's 3-2. So why is the percentage yield in this reaction greater if the pressure is higher? We'd say higher pressure, the reaction. Oh my God. The reaction equilibrium shifts to the side with the least gas molecules. In this reaction, this is the forward direction, so increases the yield. So what I mean by that is there's three gases on the left, two gases on the right. Le Chatelier said that whatever you do to the reaction, it will do the opposite. So if you use a high pressure, it says, oh my gosh, I'm going to try and make a low pressure. Which side is going to naturally be lower pressure? The side with less gas molecules colliding. So Le Chatelier says if you use a high pressure, it's going to go to the side with the least gas molecules. That's the right-hand side. And the right-hand side is always the high yield side. It's the product side. So it shifts to the products and we get a good product. So you want to use a high pressure with this reaction. In industry, the reaction is done at 450 degrees and atmospheric pressure under these conditions, the yield of sulfur trioxide is 86. So just two reasons why a higher pressure is not used. So look, they're getting 86%. If they use the higher pressure, they would get a better yield. They might get 90 or 95%. They're going to make more money. So why are they not going to use a higher pressure? Well, higher pressure comes with a few downsides. High pressure means danger of explosion. And this means you need really thick steel wall reaction vessels. Imagine a giant beaker. Think of your glass beaker in the science lab. Imagine a giant version of that made of thick metal in order to do the reaction in so that it doesn't explode. So we're going to say it is expensive and it is dangerous. High pressure can cause explosions. So all of that stuff. So you're looking at the cost, it's expensive, and we're looking at it's also dangerous. And I could go on to justify why it's expensive because you need lots of safety equipment and thick reaction vessel walls, if I could be bothered. The reaction uses a catalyst to increase the rate of reaction. The catalyst is a metal oxide, which is the most likely metal in the metal oxide catalyst. So aluminium, barium, potassium, vanadium. So what we have to do is we have to zing to our periodic table over here, folks. So hopefully you can see this. And this is our AQA periodic table. Now, which group here in the periodic table make awesome catalysts? It's this group in the middle, the transition metals. So we're looking for anything that's in here. Look, we can see vanadium is there. I think aluminium was one of them. That's group 3. No, group 3, 4, 5, 6, 7, and 1 and 2. These are not good catalysts. It's these guys here that are good catalysts. And the reason is because they have multiple ionic charges. For instance, iron can be +2 or +3, which means it can carry electrons from place to place. Copper can be +1 or +2, so it can swap. It can be oxidized and reduced, and it can take electrons and hold them for a while and then give them off. So let's zing back to the question paper. Here we are. And we're going to go aluminium. No, that's group 3. Barium, what's that, group 2 or group 1? I can't remember. Potassium is group 1. Vanadium, yes, vanadium. It is a transition metal. There we go. All right, they're the good catalysts and they make colored compounds, all because of their multiple ionic charges. Right, question 8. This question is about monomers and polymers. Compound A has an alkene functional group and an ester functional group. Figure 8 represents a molecule of compound A. So it says it has an alkene functional group. Draw a circle around the alkene functional group for 1 mark. So alkenes. What are alkenes? We're looking for the CC double bond. Can you find it? Yep, of course you can. It's right there, and that will get you a fat mark. Lovely. Let's move on. Describe what will be seen when compound A is shaken with bromine water. Well, if you have this double bond here, what happens is the double bond, if you get bromine to attack it, then what's going to happen is bromine is going to add across that double bond and get rid of the double bond. And we're going to see that double bond decolorize. Well, the bromine is orange, and we're going to see the color of the orange go. So we're going to say orange, bromine, water will decolorize. Okay, or it will go from orange to colorless. Orange. Let's go. 8.3. Figure 9 is a repeat of figure 8. Got that again. Draw a circle around the ester functional group. Now, ester functional groups, guys, those of you on the trips, obviously, that is your ester functional group. So you're looking for something along the lines of that. I don't know why I put that diagonally, or you could do it like this. It can be straight up. So actually, let's get rid of that. Could be going this way. So just don't, it's got to be a C, O, and O. It can be either way. It doesn't matter. So we're looking like that. Don't forget to go in the middle of the bond. So you're including half the bond because it's a little dash on either side. So COO dash dash, and that's going to get you the marks. Fiesta, Esther, forever. Right, 8.4. Compound A has the formula C4H6O2. Compound A is flammable. Right, a balanced equation for the complete combustion of compound A. So we're going to go C4H6O2. Now, whenever you're doing combustion, we're going to be using oxygen, folks, and we're always in complete combustion going to form carbon dioxide and water. So that is going to get me a mark for the correct writing out of that. Now I just need to balance it to get the other marks. So all you're going to do is go C4, right? Really easy. We're going to put a 4 here. So that covers my carbons. I'm then going to look at the number of hydrogens, and I've got 6. So how many waters do I need? You've got H2. I need to multiply that by 3. And so we've got 4 carbon dioxides and 3 waters. That takes care of my carbon and hydrogen. I've now got to balance the oxygen. You always balance the oxygen last. This one's a little bit harder because we've got some oxygen here, but we're going to work out the total oxygen here. So I've got 4 times O2. That's 8 oxygens in the carbon dioxide. And I've got how many oxygens here? 3. So I've got 11 O's. And we're like, oh my gosh, 11 O's. How are you going to get 11 going on here? Well, I need to get 9 here. So what we can do here is I can go 4.5 times 2. That is 9. And then I've got the 2 there, makes 10, 11. Now, some people don't like halves. If you don't like halves, double everything. So if you don't like halves, you could write it like this. Personally, I don't like doing this. This is disgusting, and I just use halves. But if you wanted to, you could do that. 9O2, and that goes to 8CO2 plus 6H2O. I don't like doing that because you got to multiply all of this and you got to times everything, double it all, and I don't like that. I like to just use halves. But there we go. Either one of them is going to get you all that 3 marks. All right, let's move on. 8.5. Many molecules of compound A join together to form polymer B. Complete the displayed formula equation which represents this reaction. So here E is the monomer. You can see it's got a double bond there. It's got an ester group there. And then complete the displayed formula. So they've just missed out here. 1 bond in the middle there. That's gone to a single bond. So we give ourselves a tick for that. 1 mark. What else have they missed out? That all looks correct. They must have missed something else out. Oh, the N. So we need to put an N as well afterwards. Because this is just 1 repeat unit. So if there's a million of these, then there's a million of these. Okay. That's a little bit of a tricky one there because you might miss the N and be studying the structure. What type of polymer is polymer B? Is it an addition polymer, condensation polymer, DNA polymer, or protein? Well, we'll go up and check. This, folks, is an addition polymer. When you get a double bond that goes to a single bond, that is an addition polymer. So I know we might think, oh, it's an ester like polyester. Isn't that a condensation polymer? The actual ester part has not been involved in the polymerization. Okay, so this is a very tricky question, but the answer is it is an addition polymer. Polymer B is a polymer which melts when heated. What word is used to describe polymers that melt when heated? It's a thermo softening polymer. Explain why some polymers do not melt when heated. Okay, some polymers, some polymers have lots of strong intermolecular forces between the chains. These are called cross links. Okay. So essentially, you get different polymers, you get these big long chains, and they line up, and some have only a few forces and they're thermosoftening, and some have like loads of strong cross links that hold the chains tightly together and require lots of energy to break, and they are the thermohardening or whatever you call those polymers. Okay, let's move on. Last question, I believe, peeps. Okay, we're looking at question 9. A student investigated the rate of reaction between zinc and sulfuric acid. The equation for the reaction is zinc solid plus sulfuric acid aqueous goes to zinc sulfate aqueous plus hydrogen gas. Figure 10 shows the apparatus. We've got a stopper here, conical flask, wunderbar. We've got sulfuric acid and we've got zinc granules. We've got the measuring cylinder here turned upside down in a water trough with a delivery tube coming out of that conical flask and into the measuring cylinder. This is the method used. Pour 50 centimeter cubes of sulfuric acid into the conical flask. Add excess zinc, bloop, 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 into the conical flask. Insert the stopper, boop, and start the timer. Beep. Measure the volume of hydrogen collected in the 50 centimeter cube measuring cylinder every 20 seconds for 180 seconds. Okay. Explain why the volume of hydrogen collected in the 50 centimeter cube measuring cylinder is less than the volume of hydrogen produced. So what do you think happens? The hydrogen is getting given off here. It's coming down here and it's going in here. Why, when we collect the hydrogen gas here, do we not get all of the hydrogen gas that's produced? Think about when they added the zinc to the acid. What they can't have had the lid in, the stopper. So they've got to chuck the zinc in and then quickly insert the stopper. In that time, some of the hydrogen gas has escaped. So there might be other possible answers. We might be able to say some of the hydrogen gas dissolved in the water, potentially, but we shall see. So I'm going to put both just in case. So I'm going to say some of the hydrogen gas escaped while they put the stopper in. And then I'm going to go some of the hydrogen gas stayed in the delivery tube. Let's say it just got trapped in the tube. Some dissolved in the water. And there we go. Hopefully that will get me 2 marks. These are all possibilities, yeah? The most obvious one is some hydrogen gases escape. That's very traditional, very common while you're putting the bung in. It's one of the weaknesses of that experimental setup. So Figure 11 shows the volumes of the hydrogen collected in the 50 centimeter cubed measuring cylinder after 40 seconds and after 100 seconds. So after 40 seconds, the gas is pushing the water down. After 100 seconds, even more gas is collected. Determine the number of moles of hydrogen collected between 40 seconds and 100 seconds. And they're being really nice to us here. The volume of 1 mole of any gas at room temperature and pressure is 24 decimeters. So this is very nice. So we need to determine the number of moles of hydrogen gas collected between 40 and 100. So I'm going to zoom in a little bit here, peeps. So what we need to do here is focus on what is the starting point? What is the starting number? So we've got 10, 15, 20, 21, 22, 23, 24, 25. So we're starting at 25 centimeter cubed. And then they're saying after 100 seconds, what has it got to? Well, it's got to 35, 36, 37, 38. What's that? 39? Yes, we're going to go 39 centimeter cubed. So the first mark here of the 4 marks is to work out the difference. So we're going to go 39 minus 25, if my eyes aren't deceiving me, is 14 centimeter cubed. And that's going to get us a mark for at least 1 mark, maybe 2 marks, because you've had to read that correctly. The 30, 20, you might get a mark for the 25 and the 39 because you've had to read this correctly. Which, I mean, it looks like it's actually more. Anyway, never mind. Let's go with 14. So 14 centimeter cubed. I now need to work out how many moles that is. Well, we know that 1 mole is equal to 24 decimeters. I really need to turn this into decimeters, or I can convert that into centimeters. So 1 mole is equal to 24,000 centimeters. So I could do that and then work out how much that is, or I could turn this into decimeters. I'm going to turn this into decimeters. So I'm going to do, when you want to turn centimeters into decimeters, you divide by 1,000. So 14 divided by 1,000 is, what's that going to be? 0.0014. Let's check it out. 14 divided by 1,000 equals 0.014. No, I'm a twit. Not quite that. 0.014. There you go. Lucky we have calculators. So it's 0.014 decimeters. So how many moles is that? Well, if that is 1 mole, this is obviously not 1 mole. It's nowhere near 24. So we need to find out how many moles it is. So we're going to go 0.014 and we're going to divide that by 24. So we're going to go divide by 24. This is for 4 beautiful marks, 5.83 times 10 to the minus 4. So it's 5.83 times 10 to the minus 4, and that is moles. So that is our final answer for 4 marks. Now it is 8.33 recurring, so I could round that to 5.8 times 10 to the minus 4. Totally up to you what you want to do. Wunderbar. Let's move on. A different student investigated how the concentration of sulfuric acid affected the rate of the reaction. 9.3. The student did a different experiment using sulfuric acid of concentration 0.4. Okay, the student calculated the number of moles of hydrogen collected after 20 seconds. So they used 0.4 mole per decimeter. What did they use up here? Did it actually tell us what the concentration was? No, No, I don't think it did. Anyway, they used zero point 0.4 mole per decimeter in this one, and they collected the moles of hydrogen after every 20 seconds. So there we go. Beautiful. We have a chart of moles. Determine the rate of reaction at 45 seconds. You should draw a tangent, 5 marks, standard form. Oh, my tangenius. Right, what we're going to do here is, oh my days, it would help if I read the question for 2 seconds. I'm going to do it up there by the graph. 45 seconds, that's all we needed to know. Give it in standard form. Determine the rate at 45. So your first mark is for locating 45 along here. That's 25. We kind of need to know, we need to know what the values of each of these baby squares are. So we're going to go, well, it's 50 seconds, 10 squares, 50 seconds. So how much is each square? So we got 50 seconds. Oh, I've done that the wrong way around, haven't I? What a twiddle. So, oh, yeah, kind of obvious, isn't it? It is 50 divided by 10 equals 5. So each square is worth 5 seconds. So 45 seconds. So 45 seconds is there because that's 25, 30, 35, 40, 45. So I'm going to draw a line up from here, guys. This is your first mark. Going to draw a line up from here. And by the way, leave your working on here, some of your working, because if they see you've done your working and you screw the rest of it up, you will get some marks. So that's going to be my first mark for drawing a point at 45 seconds. So getting that right, I'm going to get my first mark. Now what we need to do is a straight line called a tangent. This is the tangent. It's a straight line coming off this curve, and I want it to touch both axes. So you should visually, and I'm going to delete this in a second, so I'm just going to show you a wrong one. Visually, if I look either side of my line that I've drawn through that dot, I can see that I've got a bigger space here than I have here. By your eyes, the examiner wants to see roughly equal space on either side of that line on the curve. So they're not going to give, that is not a good enough line. So I'm going to try again, but bear in mind that this is really hard on the computer. Oh my days, I don't even know if that's decent. All right, I'm going with that, peeps. I'm going with that. Either side, that looks reasonably okay. So that's going to get me my second mark for drawing a tangent. First of all, I got the point, and then I've drawn a tangent there. So I've got 2 marks on the board. This is a 5 fat marker. Now what you need to do is just draw a triangle anywhere along that line and then calculate the change in y over the change in x. So it doesn't really matter where you go across that line, but it's quite nice. Look, I'm going to do 100 seconds. So I'm going to go from where it gets to 100 there. Is that right? This is going to be roughly, people. And it doesn't really matter what I do here because this is a straight line. I should just try and go where it's going to be nice and easy for me. So I think that's nice and easy for me, but I'm probably wrong. So if I go from line to line, I've gone from 25. My horizontal X is from 25 to 100. So I'm saying that that is my X axis and that is 75. Now let's calculate the Y. I've done it from roughly, I'm sure that's not exact, but 0.012 up to 0.018. Now I've got to calculate what the bloody scale is over here. You see why this is a lot of marks. So that is 0.01, 0.0, oh my days, 0.02 is the value, and then that is divided by 10. Oh my days. So I'm guessing each square is 2 times 10 to the minus 3. Yeah, but that's not too bad. So that's going to be 0.016, 0.0165, 0.0167, 0.0165. No, that's not how it works. Oh my days. 0.0164, 0.0168, 0.0172, 0.0176, 0.0178. So each ones of these are 0.0 whatever 4. So that's a fourth. So that's going to be 0.0184, 0.0188. Jeez. So in order to work out my Y, I can't believe that, 0.0188. Yeah, and then that'd be 192, 194, 0.02. Okay, right. So 0.0188, and then I'm going to subtract 0.012. That's the hardest bit there. So let's do that. 0.0188, take away 0.012, and that's why it's right at the end of the paper. Final question is what does that equal? 6.8 times 10 to the minus 3. Well, that's no good, is it? Right. So my X equals 75 seconds. My Y equals 6.83. No, 6.8. Oh my days. Times 10 to the minus 3. And what I want to do now is do change in Y divided by X. And that is going to give me my rate. So let's do that. That is going to be 6.83 times 10 to the minus 3 divided by 75 equals 9.06 times 10 to the minus 5. 9.06 times 10 to the minus 5. And then we just need to come up with the units. That is utterly brutal. And that is moles like per second. So that's moles per second, right? That is number of moles of hydrogen gas given off per second. That's actually disgusting. But you're going to get most of the marks here for drawing your tangent. And then your correctly calculated figures, i.e. this one and this one, are going to get you marks, even if your answer is not what they're expecting. As long as you have done a good effort there, you should get all 5 marks. So your answer is not going to be the same as anyone else's because it's going to depend on your tangent and the accuracy you've drawn that tangent to, but it should fall within a range. Oh, gosh. Figure 13 shows the results for the zero point 0.4 mole per decimeter sulfuric acid. Yep, we've done that. The student repeated the experiment using 0.2 mole per decimeter. So they're using 0.2 instead of 0.4 of the sulfuric acid. Excess zinc was used in each experiment. That's key. Sketch a line to show the results. You would expect 2 marks. Right. The sulfuric acid is the limiting reactant. So if I use half as much sulfuric acid, it's going to react a lot slower. So we're looking at a less steep line, and that's going to get you 1 mark. But the fact that we're using half as much of the sulfuric acid means the reaction is only going to produce half as much hydrogen gas. After all, it's the hydrogen gas that comes from the sulfuric acid. The H2 of the sulfuric acid is being displaced. So if this is 0.16, whatever that is, 8, we're going to go to half of that. And on my calculator, I'm going to go 0.168. No, 0.0168 divided by 2, and I'm going to get, I'm going to be finishing somewhere here, 8.4. So roughly, I need to take longer to get there, actually. Let me get rid of this line. So it's going to go like this. We're going to take a lot longer to get there. We're going to plateau a lot longer, and then we're going to arrive late to the party, and then we're going to plateau here, okay? So I should have taken longer to get to my straight line because this reaction is happening more slowly. Why? Because there's less collisions, but also it produces half the amount, and that is going to get you 2 marks. Now, if they had said that you're doing half the concentration, but the sulfuric acid wasn't the limiting factor, it was the zinc that was limiting, then you would be doing something like that and ending at the same point. But that's not the case. They've told us that the sulfuric acid is limiting. So we're running out of the sulfuric acid before the reaction's done. So there we go. We got half the amount. Okay, cool. Right, we're on to the final bit. Woo. Explain how increasing the temperature would affect the rate of reaction between zinc and sulfuric acid. Now, the key word here is explain. So if we were describing, we would just say increasing the temperature increases the rate of reaction, right? That's a description. And we're going to include that in our explanation for 1 mark. So increasing the temperature increases the rate of reaction, and that is going to get us a mark. But what we want to do here, that's a description, and you can do that within an explanation. Now we want to explain why. So we want to say particles have more kinetic energy. So the particles have more kinetic energy. What does that entail? I know a lot of these are on the same marking point, but I'm going to include them moving faster, more collisions. So what does that equal? That equals more successful collisions per second. Now, I've given a time. You can either do that, or it's probably even better to just get in the habit of saying higher frequency of successful collisions, or more frequent collisions, more frequent successful collisions. So the marks are more energy, more successful collisions per second, or a higher frequency of collisions. Anyway, folks, that's the end of the paper. You know what they say, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. I'll see you next time.
You're still here? It's over.